Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Unit 2 of our course. This is the introductory lecture. Now, as you know, in general, what we are talking about in this course is this current flow in small devices. And basically, the way you view it is that there's a source and a drain, and electrons want to flow through this electronic highway with states that are available for transporting electrons. In part A of the course, we talked about semi-classical transport, where electrons are viewed sort of as particles. Whereas this course, part B, it's about quantum transport. And as we have discussed, in describing transport, you not only need this mechanics, but also this what are called entropy-driven processes, the kind of things that, I guess, these contacts represent. And what we have discussed so far in Unit 1 is this Schrodinger equation, E psi equals H psi. And we discussed how you can write the H in the form of matrices, which describe this electronic highway, the levels that are available for the transport of electrons. But the point to note is, whatever we have done so far, it just describes an isolated channel, not transport really. So if you think of a range of energies, just a small window of energy dE, and with a number of states d0, this is the density of states, and you have some electrons n in there. The point is it's an isolated channel. Nothing's coming in or going out as it stands. And what we want to talk about in this unit and the next is how to include current flow, how to include this process of flow from the contacts. Specifically, the way you think about it is if there's n electrons in here, they want to go out into the contact. And that's this nu1 is the rate at which they want to go out. If the connection to the contact is strong, it will want to go out rapidly. If it's weak, it will go out slowly. So the rate at which they go out into the contact, that's this nu1n and nu2n. On the other hand, new electrons come in from the contacts. And that's this part. So how much comes in, again, of course, depends on how strong the connection is, but also depends on the density of states available inside the channel. So it's proportional to d0. So you write it as S1 d0. And as you might expect, this quantity which tells you how easily it goes out, and this tells you what comes in, they are related. Because if you have a strongly coupled contacts, electrons will go out easily, but they'll also come in easily. And we'll see there's a relation between them. But in general, you can write then dn dt, the rate at which the number of electrons inside here changes, is equal to the rate at which they go out. That has a minus sign, because if they go out, it gives you a negative dn dt. N wants to go down. Whereas the inflow, that's a positive sign because it tends to build up. And one point that causes some confusion is people often say, don't you have to worry about exclusion principle, that, well, what comes in doesn't just depend on the states available, but also on which of them are blocked because of the exclusion principle. And I'd like to mention that for elastic processes where things are flowing without changing energy, the right way to think, and this isn't obvious really, but the right way to think is that electrons just flow out and new ones come in without any reference to the exclusion principle. So it's not like what comes in gets blocked. In other words, if all these states were completely full, let's say, then the states in here would also be filled, but it's not correct to think that the electrons in there just stay there. It's more like they are continually going out and new ones are coming in. And that's the picture we'll adopt. Now, the point we are trying to make, what we want to do here in this unit, is figure out what to do with the Schrodinger equation, which describes this isolated channel, how to modify it so that this process of outflow and inflow are included. And first question, of course, is Schrodinger equation is in terms of a wave function. here we are thinking of number of electrons. How are the two related? Well, n is the psi dagger psi. You know that the psi is this wave function whose square gives you the probability of finding an electron. So if you're dealing with one electron, then the right way to interpret psi star psi, the psi square, is what is the probability you'll find it in a certain place. On the other hand, when you have lots of electrons, let's say 10,000 electrons, and there's 10% probability of finding an electron in some place, that means there will be about 1,000 electrons there. So in one electron terms, psi square is like the probability, but when you have lots of electrons, the psi square gives you the number of electrons. So, and you'll notice I've also used a psi with a tilde in it. That's because, you see, in order to understand this flow process, it's important to go to the time-dependent Schrodinger equation. What I introduced in Unit 1 was the time-independent Schrodinger equation. And by and large, you see, in this course, we are talking about steady-state flow, not transient flow. And for this purpose, usually the time-independent Schrodinger equation is adequate, and that's what we'll largely be trying to do. But in order to understand current flow, we'll occasionally have to go back to this one when we try to derive the basic equations that we'll be using in the first few lectures. The next 4 lectures we'll be doing that. I'll occasionally be going back to that one. And the connection between this and this is just that the psi tilde, the time-dependent one, is written as psi exponential minus I et over h bar. That is, if you take that form and substitute it in here, this equation will turn into that one. And the reason is there's a d dt, and when you take time derivative of this exponential function, that's usually very simple, because time derivative simply means multiplying it by the exponent, minus I e over h bar. And you can see the h bar cancels out, I times minus I is 1, and you get e. So that's how this becomes e psi. And that exponential factor just cancels out from both sides. So generally we'll be using this, but occasionally we'll go back to this, and you should be clear about the connection. Okay. Now here the question is then that as it stands, it describes an isolated channel. What do we do to get the outflow and inflow into the story? And what we'll show in the next few lectures, I guess, is that you can include the outflow by adding a term like this, and the inflow by adding a term like this. And where does this come from? Well, the right way to obtain these terms would be from the boundary conditions. That is, you say, well, you have E psi equals H psi that applies everywhere, but we are only interested in this region, so we apply certain boundary conditions. And from those boundary conditions, we can show that you get these additional terms. The boundary conditions kind of become equivalent to these additional terms. But that requires some discussion, which we won't get into right away. Actually, in the first few lectures of this course, we'll derive the basic equations, but we won't talk about how you could get these sigmas and s's from the boundary condition. That we will try to develop later using different examples, because how you exactly get the sigma and the s, again, depends a little bit on the problem at hand. So later in this unit, we'll do some 1D examples. In the next unit, Unit 3, we'll be doing more advanced examples. But for the moment, what we focus on is that given this thing, these additional terms, how they can be related to outflow and inflow. And one important point I want to make in this context is, you'll notice in this simple picture, we had 2 inflows, one from the left and one from the right. And yet here, I had put only one inflow from the left and not the other one. And there's a subtle reason for that, why it is not quite right to put both in here. It goes something like this. You see, supposing we put in both, then when you solve this equation, you'll get psi in terms of S1 plus S2. So you'll get psi is equal to S1 plus S2 times whatever. We'll see what it is later, but you could write it this way. But what you're really interested in is psi dagger psi. Right? Now, which then becomes S1 plus S2 dagger times S1 plus S2. Now, the thing is, when you multiply it out, you get 4 terms. Now, 2 of these correspond to the capital S1 and the capital S2. This is the strength of the source in contact 1, strength of the source in contact 2. But you got these 2 other spurious terms, which involve this cross product of left and right, which kind of represents sort of interference between left contact and right contact, which is never observed experimentally with normal electrons. And so, if you include terms like this, you are getting unphysical answers. So these are really never there. In real systems, whenever you have multiple sources, you never see interference between them. And in that sense, I've often made this analogy with light, that with light, if you look at a thermal light bulb, then when you have 2 light bulbs, you never get interference between them. And electrons are kind of like thermal sources. Now with light, there's also coherent sources or lasers, for example, where you can get interference between 2 different sources. With normal electrons, there is nothing quite like that. And so bottom line is, we need a theory which works directly with these products like psi dagger psi, rather than with psi. Because if you're working with an equation like this, it is not quite right to add multiple sources there, because then your theory will give you interference terms. So instead, what we do is try to develop a set of equations which applies to these products. And those basically are the NEGF equations, or non-equilibrium green function equations, that we'll be talking about. Now here again, I'd like to make a distinction between this psi dagger psi and psi dagger. The distinction, these are not quite the same thing. If these were numbers, of course, they would have been the same thing. A times B is just B times A. But these are actually column vectors. Like if you had say a lattice with 3 points, for example, then psi would be like a column vector with 3 things. And the psi dagger would be this thing, conjugate transpose. That's what the dagger stands for, conjugate transpose. So you get psi 1 star, psi 2 star, and psi 3 star. And when you multiply the 2, you just get a number, you see. And the reason is that this is like a, I guess, 1 by 3. This is like a 3 by 1. And when you multiply it, you just get one number. Psi 1 star psi 1 plus psi 2 star psi 2 plus psi 3 star psi 3. Now, by contrast, you see, if you look at psi dagger, then the 2 are reversed. So you now have a 3 by 1 multiplying a 1 by 3. And what you get is a 3 by 3 matrix. So psi 1 star goes there. Psi 1, psi 2 star, that goes there. Psi 1, psi 3 star, that goes there. So you actually have a 3 by 3 matrix. And whereas this quantity here is just a number. And how could you get this number out of that matrix? Well, you could just add up the diagonal elements. And that's what is generally called taking the trace of a matrix. So the trace of psi dagger psi and the trace of psi dagger, they are both the same. But basic thing, this is a 3 by 3 matrix, that's just a number. And anyway, so this is the quantity that we call Gn. It's kind of like this n, but then it's this matrix version of it, right? So it's like the matrix that represents the number of electrons. And there's another quantity we'll introduce, which is the strength of this source, like SS dagger. That's what we'll call sigma in, tells you what comes in. And what the NEGF equations represent is an equation that connects this to that. See? So rather than work directly with psi and s, you work with these. And the reason is that when you have multiple electrons, you cannot quite superpose their wave functions, but you can superpose their psi dagger. Now, how do you get an equation in terms of the psi dagger and SS dagger? Well, first step is, you see, if you had an equation like this, E psi equals H psi plus sigma psi plus S, you could take all these three terms on one side and write it in this form. This I is an identity matrix of the same size as H and sigma, and E is just a number, the energy. So you have this. So given this, you could write psi in terms of S by taking the inverse of this quantity. That's what's called the retarded Green's function, GR. And psi is equal to that Green's function times S. Now, if you want psi dagger, well, you have to take the dagger of this quantity. And if you remember from linear algebra, when you take the dagger of this, it gets turned around. So you first have the S dagger and then you have the GR dagger. And the GR dagger is what's called GA, the advanced Green's function. So now what we want is psi dagger. So what's psi dagger? Well, it will be like GRS and then S dagger GA. And this psi dagger then is what we call GN. SS dagger is what we call sigma N. And I've also put in this notation that's also used a lot in the literature, where what I am calling Gn is often written as minus I G less. And what I am calling sigma N is written as minus I sigma less. Okay. Now, from here then, we get this equation Gn equals Gr sigma N Ga. Or in the other notation, G less equals G sigma less Gr sigma less Ga. And these are the basic NEGF equations. This equation for the retarded Green's function and this equation for this Gn, which is like the number of electrons, the operator that represents the number of electrons. And I'd like to say a few words then about this alternative method that you see a lot in the literature. That is, what we have done here, what we'll try to do in this course is start from this one electron Schrodinger equation and get these basic NEGF equations. And this is the way I've been doing this for a long time. It's like described in my books. But the standard way that is widely used is based on the seminal work of Keldysh and other people actually back in the 60s. And that work is based on what's called many-body perturbation theory. And the reason is, you see, before the advent of nanoelectronics and mesoscopic physics, the general idea was that resistance or current flow involves dissipation. And so it is very important to include dissipative processes. And dissipative processes, of course, involve many-body interactions, because dissipation means the energy in the electron goes out into the phonons and other by interaction with the surroundings. And that requires this many-body theory, this many-body perturbation theory. And that is how these equations were originally obtained. And a lot of the literature follows that. Whereas, what we are doing is following what we have learned from nanoelectronics and mesoscopic physics, that the dissipation is kind of incidental to current flow and resistance. Much of the physics of resistance can be understood without including the dissipation. But the point I'd like to make though is that it's not like we ignore interaction completely. Because if you ignored interaction completely, then you don't quite need this NEGF method necessarily. You could use this, what's called scattering theory. But what we do, what I like about NEGF is it allows us to include interactions. And these only thing is, these interactions we assume do not lead to any exchange of energy. But as we'll see, they have an enormous amount of physics in there, these interactions. And by ignoring these energy loss processes, this energy dissipation, what it allows us to do is get the same equations. Note that these are exactly the same equations that are obtained from the many-body method. So it's the same equations, but it's done in a much more elementary way from one electron Schrodinger equation. And just to give you one example, consider a wire with a scatterer in between, a barrier, some kind, let's say a defect. in there, or an impurity. If you have taken part A of this course, you might remember that this kind of is like 3 resistors in series. The resistor at this interface, another one at this interface, and then the middle one. And so if you looked at how the electrochemical potential or the occupation of states, how it varies through the device, you'd expect a drop at one end, a drop around the scatterer, and another one at the other end. Now, if you do a coherent theory, where you ignore all interactions using quantum transport methods, what you'd get, you'd see these oscillations. The reason you see oscillations is because of what, I guess, related to standing waves that are familiar with waves. Now, but in practice, you often don't see such pronounced oscillations. And the reason is that real devices are not quite clean things like this. There's a lot of random scattering going on, which destroys a lot of the phase information. And this you can include into your theory by adding this sigma 0 and this sigma 0n, in addition to the 1 and 2, which represent the contacts. And when you include that n, you'll see the oscillations get a whole lot smaller. What's more, you'll notice there's a slope here. Why the slope? Well, because the interactions that we included also gave rise to momentum relaxation. And so they gave rise to resistance. Because the point is, resistance comes from relaxation of momentum. Now, if you want to include only phase relaxation and not momentum relaxation, that is, processes that destroy the phase of the electron, but not its momentum, and these are very common. For example, this very common interaction is electron-electron interaction. That is, one electron interacts with the other ones around it. And this destroys its phase, but it doesn't destroy momentum, because whatever momentum one electron loses, the other ones pick up. So as a collection, they kind of keep their momentum amongst themselves. Okay. Anyway, so if you include that, the momentum relaxation, you get something like this. But you can also choose these sigmas in such a way that it gives only phase relaxation. And in that case, you get something without that slope. But because of phase relaxation, of course, those oscillations have got much smaller, but there is no slope because it's pure phase relaxation. So the point I'm trying to make is this NEGF method that we'll be talking about allows you to put all this physics into the theory, but through this sigma 0, something that a normal coherent theory doesn't allow you to do, because coherent theory is just based on 1 and 2. But we are not including dissipative processes at all. And that's what, I guess, keeps the overall framework simpler, because dissipative processes generally require a deeper discussion of these of many-body interactions. And we'll do a little bit of it at the end of Unit 3. But by and large, what we'll be talking about, we ignore dissipative processes. Okay, so with that long introduction then, we're ready to get on to it, get on to the real stuff. And what I should point out is that the next 4 lectures here are kind of about developing these equations. You know, the basic idea that you modify the Schrodinger equation, and then you have the NEGF equations which relate the bilinear products, etc. That's what we're doing in this these next 4 lectures. And after that, what we do is look at examples. And to some extent, the two are disjoint. In the sense, here what you see is how these equations come about. Here you see how to apply it to simple 1D examples. Whereas in Unit 3, what we do is more advanced examples. So you may want to kind of look at this quickly, get on with it, look at the examples, and then, if necessary, come back and look at these 4 lectures. Okay, so with that, then we are ready to get on with 2.2. Thank you.